Hi everyone, let's do some math riddle. The title of this riddle is, where did the extra dollar come from? Let's say I have $50 and I recorded the amount I spent and my balance. Let's say I spent $20. My balance therefore would be 50 minus 20 equals $30. Then from the $30, I spent $15. My balance would be 15. And then I spent $9. My balance would be 15 minus 9 equals $6. And finally, I spent the remaining $6, and so my balance would be $0. If I get the total of each column, 20 plus 15 plus 9 plus 6 gives us $50 for the spend column, and 30 plus 15 plus 6 plus 0 gives us $51. What happened? There is an extra $1 here. Where did that extra dollar come from? You can pause the video and analyze this riddle. Let's solve this problem together. In order for us to solve this riddle, let's use extreme values so that we can see where the inconsistency lies. Let's say I spent $1, my balance would be 49. 50 minus 1 is 49. From this 49, let's say I spent again another $1, so my balance would be 48. And I spent again another $1, and my balance would be 47. And finally, let's say I spent that remaining amount of $47, and so my balance would be 0. If we add the spend column, we get this $50, which is consistent with the amount I started with. But notice that in the balance column, the total would be $144, which is clearly way more than the $50 that I have here. So this means that adding the spend column would always result to the amount I started with, but it is meaningless for us to add the balance column. This will not always total to $50. On the other hand, let's say I have a different value. Let's say I started with $50 and I spent the entire $50 right away, and so my balance would be 0. Therefore, the total of this spend column is 50, and for the balance, it's 0, which is way different than this $50. So I hope at this point it is now clear that adding the balance column is meaningless. This will not give us the same values over and over because depending on the amount you spent, this balance column would fluctuate. And when you add those results, you will not always get $50 for the sum. The only column that's meaningful to add is the spend column. There is no use of adding this balance column. And that explains why there appears to be an inconsistency right at the beginning when we presented the riddle. 3 friends went to a store to buy a laptop. The sales clerk said the laptop costs $300. So each man shared $100. As they are leaving the store, the manager said the correct price of the laptop is only $250. So the clerk returned $30, 10 to each of the 3 men, and pocketed the remaining $20. So effectively, each paid only $90, and 3 times 90 is $270. And the clerk took $20. The total is $290. There's a problem. Where is the missing $10? You can pause the video and see if you can solve this math riddle. And thanks to TechMath for this problem. Now let's solve this problem together. The key to solving this problem is to follow the flow of the money. So here is the flow of the money. The 3 men actually spent $270, not 300 but 270, because $10 were returned to each of the 3 men. So each man only spent $90, or a total of $270. Now, where does this money go? $250 of this $270 went to the store to pay for the laptop, and the remaining $20 was taken by the clerk. So a total of $270 fully accounted. So there's no problem here. Nothing is missing. Now the problem in the puzzle lies in the fact that we added this $270 to the $20 that the clerk took, and that gave us a total of $290. Now this is a wrong accounting because we are mixing up the numbers. The total money spent is $270, and that $270 are accounted this way. The $250 went to the store to pay for the laptop, and the $20 was pocketed by the clerk. So we are not looking at the $300 anymore. And so it is incorrect to add this $270, which is the total amount spent by the three men, and look at this $20 as separate from this $270, because actually this $20 is part of this $270. So you cannot add this part of this money to itself. The correct analysis is this $270 was broken down into $250 that went to the store and the $20 that went to the pocket of the clerk. So nothing is missing. Some of our followers are debating on how to solve this viral problem. And so we created this video. Here is the problem. A man buys a goat for $60. Then he sells it for $70. Then he buys it again for $80 and sells it again for $90. How much did he make? You can pause the video and see if you can analyze this math riddle. And if you already know your answer to this problem, please write them in our comment section. Now let's solve this problem together. Let's begin with the man buying this goat for $60. From the point of view of the man, since he bought the goat and the money is going out, let's denote it as -60, and the color pink means the money is going out. It's an expense. Then the same goat is sold by the man for $70. And so at this point, the man has a profit of $10. Then after selling the goat, the man buys it back for $80 now. And so the man has to pay an additional $10 in order to buy the same goat. Then he sold the goat for $90. So that means he has a profit of $10. So the main question now in this riddle is, how much did the man make? Does he make $30, $20, $10, or zero or break even? Now, problems like this where you are keeping track of the profit or the running balance is oftentimes very confusing. And the best way to analyze this is just to gather all your expenses and gather all your revenues. So let's group together all the expenses. The man bought it for $60, so that's a money that's going away. And the second time, he also bought the same goat for $80. So the total expenses is -60 plus -80 equals -$140. Then the first time he sold the goat, he sold it for $70. And the second time he sold the goat, he sold it for $90. So there is a total amount of $160 for his revenue. And subtracting revenue minus expenses, that gives him the profit of $20. So the answer to this riddle must be $20. Now, why are there so many people answering 30, 10, or 0? Let's analyze their thinking process, how they arrive at those numbers. So for those who answered $30, this is what they're thinking. The man spent $60 to buy the goat for the first time, and at the end of all these transactions, he pocketed $90, and therefore from the capital of $60 to the final revenue of $90, there is a profit of $30. Now, what's the problem with that approach? The problem with that is, notice that somewhere here, when he sold the goat for 70, he has $70 now. But when he bought it back for $80, he has to spend an additional $10 because he has only $70 here. He needs another $10 from his own money to be able to afford to buy it for $80. So in effect, he is not only spending $60, but he is also spending another $10, a total of $70. And so 90 minus that $70, the profit is $20, not $30. Now, why are there some people answering $10? This is the reasoning. You have a profit here of 10, you lose $10, that's 0, and then you profit again $10, so the final profit is $10. There's a problem also in this reasoning because this $10 and this $10, they are different money. This negative 10 here is an additional money from the man, and this $10 is not this negative 10 here. And so you cannot just subtract these two because you need to keep track where those monies are coming from. Now, why are some people answering break even? Their reasoning is because you buy it, you sold it, you buy it, you sold it, you buy it, you sold it. And in all those transactions, there is the same profit and loss. And so they are thinking, after all these transactions, nothing is gained, nothing is lost. Although some people are also asking, you have to pay for the tax, you have to pay for the food of the goat, and some of the other expenses that come with owning the goat. But in this riddle, we disregard all those other tiny details. We just focus on the amount spent and the amount received from all the transactions. And so to reiterate our answer is 20 because in order to analyze this, just add together all those expenses, and that is equal to $140, and add all the revenues, and that is equal to $160, and subtracting the revenue minus the expenses, that gives us a profit of $20. Let's call this problem as the crazy rich uncle's lacquer problem. Here's the situation. Your rich uncle just passed away. You and your 99 nasty relatives were invited to the reading of the will. Your uncle wants to give you the inheritance, but knowing your other nasty relatives, he devised a plan of possibly giving you the entire inheritance because he knows that you are good at solving math puzzle. And so the family lawyer started reading the will. In the will, your uncle said, I have created a puzzle. If all of you answered it together, then you will share the money evenly. However, if you are the first one to find the pattern and solve the problem without going through all the legwork, you will get the entire inheritance for yourself. Then the family lawyer signaled to each one of you to go down the basement containing 100 lockers. The puzzle says that ear number 1 is going to open every locker. Ear number 2 is going to close every second locker. Ear number 3 is going to change the status of every third locker. If it is open, he's going to close it. And if it is closed, he's going to open the locker. This pattern will continue until all 100 of you have gone. The words in the lockers that remain open is the clue to crack the code to open the safe. And to better understand this clue, let's do some dry run. First, ear number 1 is going to open every locker. So from pink, all these lockers will be turned into color blue. So all lockers are now open. Second step is ear number 2 is going to close every second locker. So 2 will be closed, 4 will be closed, and all the even numbered lockers will be closed by ear number 2. Then ear number 3 is going to change the status of every third locker. So this number 3 locker from open will be closed. This number 6 from closed to open. This number 9 will be turned to pink. This number 12 will be turned to blue. 15 to pink. 18 to blue. And every third locker will be changed to its opposite color. So after ear number 3, this would now be the setup of the locker. So if one of you can solve the puzzle without going through all this legwork, then you will be rewarded the entire inheritance. And this pattern will continue until all of you have gone. The words in the lockers that remain open is the clue to crack the code to open the safe. Now, before any one of your relatives can start doing all this legwork, you volunteered that you already know the answer to this puzzle. So let's pause the video and see if you can figure out which lockers will remain open after all the 100 relatives have done the steps as described. You can write your answer in our comment section. Now, let's solve this problem together. In our analysis, let's just focus on the first 10 so we can have an idea of how the pattern unfolds. We are done with your relative number 3, and this is the positioning of lockers number 1 to 10. So for your relative number 4, this is number 4, this will be changed to blue. Number 8 will be changed to blue, and it will continue to the other lockers until 100. But we are just interested in seeing the pattern for lockers number 1 to number 10. Then let's proceed to your relative number 5. Again, he or she will change the status of number 5 and all multiples of 5. So next is locker number 10. And so on until the 100 lockers. Then for year number 6, he or she will change number 6, number 12, and so on, but they are already hidden in this analysis. Then for the 7th relative, he or she will change locker number 7, number 14, and so on. And number 8 will change the status of number 8 locker from blue to pink. And then number 9, locker number 9 will be changed, and then all the succeeding multiples of 9. And for number 10, this locker number 10 will be changed. Now, at this point, what do you notice? What are the properties of those lockers that remain open? You have 1, 4, and 9. What kind of numbers are they? Notice that there's a pattern. When a locker is moved even number of times, the resulting status would be a closed locker. And when the locker is touched odd number of times, the locker status at the end would be open. For example, number 1 will only be touched by relative number 1, and so it remains open. Locker number 2 will be touched by number 1 and by number 2, so there's an even number of touches, and the status here is closed. For locker number 3, this will be changed by number 1 and by number 3 himself or herself. That's even number of touches, so it's closed. For number 4, it will be touched by number 1, it will be touched by number 2, and by number 4 relative. So there are 3 touches, odd number of touches, and that result to an open locker. For number 5, this will be touched by relative number 1 and relative number 5. So there are 2 touches. That's even number of touches, so it's going to be closed. Let's jump to number 9. Number 9 will be touched by relative number 1, by relative number 3, because 9 is a multiple of 3, and by relative number 9, himself or herself, and that is 3 touches, which is an odd number of touches, and so number 9 locker is open. And so all those locker numbers that are touched odd number of times are the ones that will remain open by the end that all the 100 relatives perform the process as described in this puzzle. To analyze it further, let's consider, let's say, locker number 64. For locker number 64, it will be touched by number 1, number 2, number 4, number 8, number 16, number 32, and number 64, because 64 is a multiple of all these numbers, or 64 has the following numbers as its factors. And there are how many factors here? You have 1, 2, 3, 4, 5, 6, 7. 7 factors corresponding to the number of touches, and odd number of factors resulted to an open locker. And so we predict that locker number 64 must be open. This means that the lockers that will remain open will be those lockers with odd numbers of factors. And those numbers are the perfect squares. Why? Let's analyze. Note that factors come in pairs. For example, 4 can be written as 1 times 4, that's one pair, or 2 times 2, that's another pair. But for the number of factors, we have 1, 2, and these 2 are the same numbers, so we just count it once, and therefore we have 3 factors here. That happens when we have a perfect square. If the number is not perfect, then we cannot have the same number multiplied together to get that number. And therefore, you will have 2 factors here instead of 1 count. So, For perfect square, there is repetition of factors and they are only counted once. So for number 9, we can write 9 as 1 times 9 or 3 times 3, and we have 1, 2, 3, 3 factors. The same with 16. 16 is 1 times 16, 2 times 8, and 4 times 4. Because it is a perfect square, you have the same factors here multiplied by itself. We have 1, 2, 3, 4, 5 factors, and this is an even number of factors. So that means that those Laker numbers that are perfect squares are the ones that will be touched odd number of times, and they are the Lakers that will remain open by the end of year number 100. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lockers that remained open. And whatever are the words in those open lockers will be the clue to find the code for the safe. And here is now the code. The code is the first 5 lockers touch only twice. So we want to find out which are the lockers here that are touched only twice. And what are those locker numbers? Those locker numbers are the prime numbers, because prime numbers contain only 2 factors, 1 and itself. And the first prime numbers among these 100 numbers are 2, 3, 5, 7, and 11. And that opens the safe. So our final answer, therefore, in this puzzle is the code is 2, 3, 5, 7, 11. And that is the key to this problem. A 300-foot train traveling at the rate of 300 feet per minute must go through a tunnel that is 300 feet long. How long will it take the train to travel through the tunnel? Let's visualize this riddle. This is a 300-foot train, and this is a 300-foot tunnel. The goal is for the train to fully emerge to the other end of the tunnel. Our goal is to know how long will it take for the train to travel through the tunnel. Letter A, 1 minute. Letter B, 2 minutes. Or letter C, 3 minutes. You can pause the video and see if you can solve this math riddle. And if you already know the answer to this riddle, please write them in our comment section. Now let's answer this riddle together. So let's simulate this train going through the tunnel. And here is our simulation. Let's repeat it. If our point of reference is the back of the train, notice that this point must travel all the way to this point in order for the train to fully emerge to the other end of the tunnel. And so this red arrow represents the total distance traveled by the train. On the other hand, if our point of reference is the front of the train, notice that this front of the train must go through all the way up to this point in order for the back of the train to emerge outside the tunnel. So in both ways, the distance traveled must be 300 plus 300 equals 600 feet for both the red and the purple distances, representing the distance traveled either by the back of the train or by the front of the train. And so contrary to the intuition of many students, where they think of the distance traveled to be 900 feet, the answer to this problem is not 3 minutes, but rather 2 minutes. The train will travel 1 minute to cover the first 300 feet and another minute to cover the remaining 300 feet. So our final answer is 2 minutes. A prize is placed under one of the 5 options. Sheila is privately told the shape of the object, and Colin is privately told the color of the object. Both Sheila and Colin are mathematicians who use perfect logical reasoning, and the initial setup is a common knowledge. The host then said, "Do either of you know where the prize is?" And there was silence. The host then asked again, "Do you know now?" And still there is silence. The third time, the host asked, "Do you know now?" Both Sheila and Colin said yes. The question now is, where is the prize? You can pause the video and see if you can solve this problem. And if you already know where the prize is, you can write your answer in our comment section. Now, let's solve this puzzle together. Let's create two columns, one for Sheila and one for Colin. And both Sheila and Colin are selecting from 5 possible answers. Let's begin with the first step here. The host asks both Sheila and Colin if each of them know where the prize is, but both of them were silent. The implication of that is, since Sheila knows the shape, if the correct answer is a square, then Sheila would have known already the correct answer right at this first step, because there is only one square, but she was silent. This implies that this pink square is not the correct answer. Now for Colin, who knows the right color, and there are only 3 colors here. We have green, we have pink, and we have this blue. If the correct color is blue, then Colin would have known already the correct answer. He could have chosen this blue circle, but he did not. So that means this blue circle is not the correct answer. And since both Sheila and Colin are mathematicians who use perfect logical reasoning, then Sheila would be able to know that since Colin did not select the blue circle, Sheila will also be able to figure that out, that this blue circle is not the correct answer. The same explanation applies to Colin for figuring out that this pink square is not the correct answer. And so we can now eliminate these 2 objects. Next step, the host then asks, "Do you know now?" And still there's silence. So from the point of view of Sheila, who knows the shape, and there are only 2 shapes here, if the correct answer is a circle, Sheila would have known the correct answer already because there is only 1 circle here. But she was silent. So this green circle must be the wrong answer. On the other hand, from the point of view of Colin, who knows the right color, if the correct answer is pink color, then Colin would not be silent at this stage because there's only 1 pink. The fact that he is silent says that the right color is not pink but rather green. And he cannot decide because there are still 2 shapes with green color. And so we can now eliminate this pink triangle. And Sheila, being a mathematician with a perfect logical reasoning, will be able to figure out that this is not the correct object. The same with Colin figuring out that this green circle is not the correct object. And so we are now left with this green triangle, both for Sheila and Colin. And that is the reason why at step number 3, both Sheila and Colin said yes. They know the answer, and the prize is hidden under this green triangle. We are given here a red cross, and we would like to cut this red cross into 5 smaller pieces that can be reassembled into 2 identical smaller blue crosses as shown in this figure. You can pause the video and see if you can solve this puzzle. And if you know the answer to this puzzle, please write them down in our comment section. Now let's solve this problem together. In order to quantify how big the 2 identical smaller blue crosses that we want to form, let's compute for the area of this red cross. You can think of this red cross as composed of 5 identical smaller squares. And if the side of this square is S, that means the area of one of these squares is S squared. And since there are 5 of those squares, then the area of the big cross is represented as 5S squared. Now, if you want to create 2 identical crosses from this one big red cross, that means the area of each of those 2 identical crosses must be half the area of this big red cross. And we can achieve that if we are going to create another cross that is scaled down by a factor of 1 over square root of 2. And this is the cross that we want, the blue cross is a scaled down version of the red cross by 1 over square root of 2. So if the area of the big cross is 5s squared, then the area of the small blue cross must be 5, and we replace this s by 1 over square root of 2 times s, which is s over square root of 2, and we square. Simplifying, this gives us 5 times s squared is s squared, but square root of 2 squared is equal to 2. And clearly, 5s squared over 2 is 1/2 of 5s squared. So the area of the small cross here now is just half the area of the big cross. So we are now sure that this blue cross has an area that is half the red cross. But the problem now is, how are we going to cut this red cross into 5 smaller pieces that can be reassembled to create 2 identical smaller blue crosses? So what we are going to do is, we are going to tilt the blue cross so that each of these corners are touching the edge. And we are now looking here at 5 pieces. Here is the first piece, here is the second piece, the third, the fourth, and of course the fifth is this cross at the middle. The other part of the puzzle is to reassemble these 5 pieces. So let's reassemble now these 5 pieces into 2 identical smaller blue crosses. So let's begin with this bottom piece here. So we transfer that here. Next is, let's move this second piece down here. And let's put this third piece here. And lastly, this fourth piece somewhere here. Notice that we now have here a cross. And since the area of this blue cross that's left is 1/2 the total area of the red cross, then we know that these remaining parts must also be identical to this other blue cross. We now have these 2 identical smaller blue crosses, and we now have 1, 2, 3, 4, 5 pieces as required in the problem. And to check that these 2 really are identical, we can superimpose the 2 and we form identical crosses. We are given this numeric lock with a 3-digit key. And the way to open this lock is for us to follow this logic stated in these 4 statements. The first one is, one number among 2, 6, and 5 is correct and is placed well. Second, all these numbers 3, 8, 7 are wrong. Third, one number among 2, 3, and 4 is correct but wrongly placed. And lastly, 2 numbers from 4, 7, and 1 are correct but are wrongly placed. You can pause the video and see if you can solve this logic problem. And if you know the answer, you can write them in our comments. Now let's solve this problem together. Let's first look at the numbers that we can choose from. You have 1, 2, 3, 4, 5, 6, 7, 8. The digit 9 is not among the options. So that means for the first column, we can choose from digits 1 to 8, the same with the second and the third column. The first statement says that one number is correct and is placed well. It could be 2 in the first digit, 6 in the second digit, and 5 in the last digit. At this point, it is best to eliminate first those numbers that we know are not solutions to our puzzle. So let's go to the second statement. All numbers are wrong. So we can eliminate this 3, we can eliminate the 8s, and we can eliminate the number 7s. Based on statement number 3, one number is correct but wrongly placed. So 2 could be correct, but if 2 is correct, it should not be in the first column. So we can eliminate 2 in the first column. 3 is already eliminated here. And then 4 should not be in the last column based on statement number 3. So let's eliminate 4. Next, based on statement number 4, 2 numbers are correct but wrongly placed. So if 4 is correct, 4 could not be in the first column. So let's eliminate 4 here. 7 is already eliminated in all columns. And 1 could not be in the last column. Then let's go back to our first statement. One number is correct and is placed well. Since 2 is already eliminated, this 2 could not be here. So 2 is also eliminated. So based on statement number 1, 6 and 5 could still be our candidates. Next, let's go back to the last statement. Two numbers are correct, and we already know that 7 is not correct. So we know that 4 and 1 are the correct digits, but they are wrongly placed. That means 4 could not be in the first column. That leaves us only 1 in the first column. So that means 1 is now the first digit in the puzzle. Now, by knowing that 1 is in the first column, we are left with number 4 as the only correct digit based on statement number 4. So 4 could be in the second column, 4 could be in the last column. But notice that 4 cannot be in the last column based on our elimination previously. So we have nowhere to place 4 but in the middle column. So 4 must be the middle digit. And then going back to the first statement, one number is correct and is placed well. We know 2 is not that number, 6 is not that number because we already know that the middle digit is 4. So we are left here with 5 as the only correct answer based on statement 1, and 5 is in the right place value. So 5 must be the third digit. And so we now have the answer to our puzzle. The code to open this numeric clock is 1, 4, and 5, and that opens the lock. We are given here a division problem, but all the digits are hidden behind these boxes except only 2 digits, 8 and 0. The 0 here tells us that there is no remainder in this division operation. We are asked to use logic to reconstruct this division problem, and our main goal is to find what is the value of this 3-digit divisor. This problem is easier than it appears, and this problem is considered as the most popular problem published in the American Mathematical Monthly in 1954, and credit to P.L. Chesin from the Westinghouse Electric Corporation. You can pause the video and see if you can solve this math problem. And if you know the answer to this problem, you can write them in our comment section. Now let's solve this problem together. First, let's observe this part here. Since the first product here stops at this digit, then we can think that there is a digit here, and our quotient must be 1, 2, 3, 4, 5, 5-digit quotient. So we start here at the question mark, multiply by this 3-digit divisor. The result is a 3-digit product. Then we subtract. Normally, we just have to bring down 1 digit here, but notice that there are 2 digits that are brought down here. This only happens when the quotient here is 0. So that means there must be a 0 here. Notice that the same pattern happens here also. Instead of just bringing down this digit, 2 digits were brought down. So the implication of that is there is also a 0 in this digit. And then there must be a last digit here. Now, since there is only 8 here as our given digit, if this 8 is multiplied by this 3-digit divisor, the result is this part here, which is also a 3-digit number. And notice that this 8 times what number gives us the minimum 4-digit number, because if there are 3-digit numbers here, this cannot exceed this minimum 4-digit number. And we know that that missing factor must be 125. So if 8 times 125 is a 4-digit number, and in here we only have 3 digits, then this divisor must be less than 125. And so we now have our first conclusion here. This 3-digit divisor must be less than 125. It could be 124 or less. Next, let's look at this last digit here. This number here times this number that must be less than 125 resulted to this 4-digit number. And so we said that 8 times a number less than 125 is a 3-digit number. In order to get a 4-digit number, this last digit here must be 9. Just like that, and we already know these 4 digits of the quotient. Now, how do you find this first digit of the quotient? Let's just focus ourselves on this part. So a number times a divisor that's less than 125, that means 124 or less, resulted to this 3-digit number. So clearly, 9 could not be a possible candidate because 9 times a 3-digit number resulted to a 4-digit number, and we have here 3-digit product. So 9 is not that digit. So our candidates are numbers less than 9. It could be 8, 7, or less. Now let's try 7. 7 times 124 is 868. So if we assume that we have 868 here, and the difference between this 4-digit and 868 is this 2-digit number, let's assume that this 2-digit number is the maximum. Let's say 99 is the maximum 2-digit number. If we add 868 plus, suppose this is 99, the maximum value that we can get is 967, and this is relevant. Why? Because notice that we have here a 4-digit number. So 967 is just a 3-digit number, which means that 7 or any number less than 7 cannot be this first digit number. And therefore, this first digit number could not be 7 or less. It could not be 9. We are left with only one choice, and that number is 8. The first digit must be 8. And so going back to our original problem, we now know that this question mark is equal to 8, and so the quotient is 80,809. And this divisor must be a number less than 125. Let's try 124 first. So this quotient times 124 is this 8-digit number. And let's try the other number less than 124, because our candidates are all whole numbers less than 125. So let's try 123. This quotient times 123 gives us a 7-digit number. But clearly, this number must be an 8-digit number. So we can now deduce that since the divisor must be 124 or less, and 123 or any number less than 123 resulted only to a 7-digit number, we now conclude the divisor of 124. This number here inside must be this 8-digit number. So we now know the quotient, we now know the divisor, which is what we are looking for in this problem, and we can now complete the puzzle this way. So if we are going to reconstruct this division problem, this is now the exact reconstruction, and the answer to this puzzle is 124. The divisor is 124. And we accomplish this all by just using simple logic. Hi everyone, let's do some math magic. And here's the magic. First, we are asked to choose any 3-digit number. In my case, let me select 143. Then step number 2 is repeat the digit in the same order to make a 6-digit number. So my 143 becomes 143,143. Next is to divide the result in step number 2 by 7. So 143,143 divided by 7 is 20,449. You can use your calculator to do this division. Next, divide 20,449 by 11. The result is 1,859. And finally, divide 1,859 by 13, and the result I got is 143. Now notice that this 143 is just the same as the number I started with. How about you? Do you also get a result similar to the first number you started with? Let us know in the comment section. Now notice also that since the product of 7, 11, and 13 is 1001, you can also divide 143,143 by 1001, and still you will get the same result, 143, which is the same as the first number you started with. Now the main question here is, why does this magic work? So before you try this with your friends, let me explain to you the mathematical reasoning behind this magic. So generally, let's select any 3-digit number, and let's represent the number as A, B, C in expanded form. Since A is in the hundreds position, B is in the tens position, and C is in the ones position, ABC can be expanded as 100A plus 10B plus C. So in our case, 143 can be written as 1 times 100 plus 4 times 10 plus 3 times 1. Now, step number 2 is to repeat the digits in the same order to make a 6-digit number. So our ABC becomes ABC, ABC, which can be written in expanded form this way. So again, this is for the ones digit, the tens, the hundreds, then this is for the thousands, 10,000s, and 100,000s. Step number 3 is to divide by 7, then by 11, and then by 13, which is just the same as dividing by 1001 once. So let's do the division. We want to divide this expanded form of our 6-digit number by 1001. But first, notice that 100,000A plus 100A can be combined as 100,100A. Also, 10,000B and 10B are like terms which can be combined as 10,010B, and 1,000C plus C is 1,001C. Let's divide this by 1,001. So divide the first term by the divisor to arrive at 100A. Divide the second term by 1,001 to get 10B. And divide 1,001C by 1,001 to get C. Notice now that 100A plus 10B plus C is the expanded form of the number with digits A, B, and C. And going back to our original representation, we started with the number ABC to be our chosen 3-digit number. And by following the process in this magic, the final result will go back to that original number ABC. And that is now the reasoning why this magic works. So you can try this magic with your friends and see how amazed they will be.